including the distributed mass of bodies. Up until now, typically we've been neglecting the weight of beams themselves when we are considering the kinetic energy in the systems that we're dealing with. We were typically saying that the beam's mass was going to be much less than some point mass or some heavy load that it was supporting. While this simplified our analysis by not having to consider the mass of these deformable objects, it's not necessarily accounting for all the mass in the system that is going to be important. Now, why did we ignore this? As we're going to see, accounting for the mass of these deformable objects is going to add some difficulty while we're in our modeling step to include it into the equivalent mass. But if the mass of the beam or the deformable object has a non-negligible amount of mass, then this could have a pretty big influence on the behavior of our system because it could really impact what the equivalent mass in the system is. So how do we go about including the mass of the beam itself when our beam is a deformable object? Well, as we're about to see, it's not as simple as just finding the center of mass of the beam and putting all of the weight at that point. It's going to have to do with how the beam flexes because the kinetic energy throughout the beam is not going to be uniform, and that's what just putting everything at the center of mass would be implying. What we're trying to do is find an equivalent amount of mass that we could put at a desired degree of freedom that's going to have the same kinetic energy as the original beam. So what we can do is, with an integration step, we can find the total kinetic energy in our beam and then equate that to some equivalent or effective point mass that we can put at a desired degree of freedom. So what does this look like graphically? So if we have our original beam here, and I'm going to break it down into small pieces. So each piece I'm going to say has a width of dx, and it's going to have a density, a linear density of rho. So the linear density would be like in kilograms per meter or slugs per inch, something like that. So that density rho is going to be taking into account the width and the height of the beam. Now, in the case where we have a uniform beam, where it's homogeneous, then the density, the linear density, is just going to be m over L. So I'll simplify it to that for right now. Each one is going to deflect by some amount y. And the amount of deflection is going to be dependent on where in the beam we are. It might deflect more to the left or the right or in the center. It's going to depend on the boundary conditions of the beam. Is it fixed? Is it free? Things like that. So what we're interested in is if I just take one of these, so let's just look at this one, I want to know what one of these little tiny squares, what its kinetic energy is going to be. So kinetic energy is going to be generally 1/2 mv squared. So it's going to be 1/2 times the mass of just this little piece. Well, the mass of the piece is going to be its linear density times its length. So I'll spread that out just a little bit there. So that rho dx is the mass of one little piece. And then I want to know the velocity of one little piece. Well, if I know that the position of this piece is also y of x, then its velocity is going to be y dot of x. And because it's going to be the velocity squared, I'm going to need to square that. So potentially rho could also be a function of x, but we're just going to go with this homogeneous type of beam here. So this is going to give us 1/2 times m over L times the y dot squared times dx. So that's the kinetic energy in one of these pieces. Since I want to know what the total kinetic energy is in my beam, I can integrate this over the length of the beam and add up all of these little pieces to get that total kinetic energy T. Now, what's the goal here? What do I want to get to is I want to treat it like a massless beam with all of it, let's just say that this is where we are interested in having our degree of freedom, which we'll call delta. I want to know what should the effective mass be where these two systems are going to have the same kinetic energy. Now I'm just talking about the beam here. There might be other masses as well, but I'm just trying to make a effective mass equivalency for my beam. Well, since the left-hand side I've already been able to calculate, so that's going to be, I can pull out a 1/2, and if m and l are constant, I can pull that out too. This y dot x squared dx is going to be left on the inside, will be equal to, now in this picture, the kinetic energy, well, all of the mass is going to be located at that effective mass point. So 1/2 times the mass of this system times the velocity of this system. So if delta is the displacement at that degree of freedom where I'm placing the mass, then delta dot will be the velocity, and that will get squared. So again, the premise is, how can I take all the mass of this beam and concentrate it at one point so that these two systems, the simplified on the right and the true one on the left, have the same total kinetic energy? And what I'm looking for is, what will the effective mass be such that the two systems do have the same kinetic energy? On the subsequent slides, we'll deal with how do we find that effective mass. But first, we can have systems that are not homogeneous. The density, the linear density, could vary with x. So we can have just this slightly more broad and general equation for the kinetic energy, where we use the rho of x, if it's, again, changing as we go from the left of the beam to the right of the beam. So if we also have a point mass in the system, as we're going to be seeing, then the equivalent mass is going to be the effective mass. That is the mass from adjusting or accommodating for the beam's kinetic energy itself, plus the point mass in our system. So together, that will calculate our equivalent mass. So again, the effective mass, we have to calculate how much that effective mass is such that our simplified equivalent system has the exact same kinetic energy as the deformable beam does. So we want to calculate this effective mass. So we have this relationship here. We know that the two systems must have the same kinetic energy, so we can simplify this a little bit. So what we can do is, first of all, they both have a 1/2. We can take those off. The m over l, for now, I'm just going to be presenting if we have a homogeneous beam. Then the m over l is able to come out, because neither of them are going to be a function of x, which is what we're integrating with respect to. And we want to solve for MEF, or the m effective here, so we can divide through by that delta dot. So I have a delta dot squared on the bottom, and I have my integral on the top, but this delta is constant. So what is the delta? The delta is the deflection at the degree of freedom we're trying to track for the equation of motion. So y of x is going to be the general deflection of the beam as we go from the left to the right. Delta is really the y of x evaluated where x is located at the degree of freedom we are trying to track. So since delta and delta dot therefore are going to be constant, or in that they are not functions of x, we can put it into that integral and then combine this. So if we want to find the m effective for a homogeneous beam, at least, this is the integral that we can evaluate, is going to be that general beam deflection equation, y of x, over the delta, which is the deflection, or in this case, the velocity at the degree of freedom we're tracking. Then we square it and integrate it, and we can find what that effective mass will be.